All right, let's get started. Welcome to the deep dive. Today we're going to be tackling something a little different. We're going to be diving into some physics.
Hmm.
Specifically, we're talking about the dynamics of a block that's attached to a spring on an inclined plane.
Right.
Ramps and springs sounds pretty basic, right?
Yeah, you would think so, but
Trust me, there's a lot more to it than meets the eye.
a lot more.
So we're going to explore the forces at play here,
Mm.
see how they make this system,
Right.
really tick.
Dick.
And we're not just, theorizing here.
Right, right.
We've got a secret weapon,
Yeah.
a physics simulation model
Ah.
developed by Wolfgang Christian,
Yeah.
and it's called, appropriately, block and spring on an inclined plane.
It's a pretty straightforward
It
name.
is, it is. But it's
Yeah.
like having a virtual lab, right?
Mhm.
Where we can see how changing things like the angle of the ramp
Yeah.
or the spring's strength affects the block's movement.
It's a really cool visual tool to really get a sense of
Yeah.
how these forces interact.
Okay, so I'm picturing it. I've got the ramp, block, spring. It feels very Wile E. Coyote,
Aha. I can see that.
but also kind of zen in a way.
Yeah. Yeah, absolutely.
So what are the forces in this little world we've created here that are going to make things interesting?
Well, first up, we got to have gravity, right?
Yeah.
It's that constant pull towards the center of the earth,
Yeah, can't escape it.
You can't. But on an incline, gravity doesn't just pull straight down.
Oh, interesting.
It actually has a component that pulls the block downwards along the ramp.
Oh,
So it's almost like gravity's playing a little trick, pulling the block sideways.
I see. So gravity wants that block
Yeah,
to slide down the ramp.
absolutely.
But what's stopping it? Or at least trying to?
Well, that's where our next player comes in. Friction.
No, of course.
Friction always wants to be the party pooper. It's always resisting the block's motion, whether it's, trying to get moving or if it's already sliding.
So it's like friction saying, not so fast, block.
Exactly. Hold your horses.
Okay, but what about the spring?
Yeah.
What role does it play in all of this?
Well, the spring is kind of like the homebody of the group.
Oh,
It's always trying to pull the block back to its equilibrium position, back to its natural resting length.
Gotcha.
You can think of the spring like a rubber band.
Okay.
You pull it, and it wants to snap right back.
Yeah.
Same idea here.
All right, so we've got gravity pulling the block down,
Yeah.
friction trying to stop it,
Yep.
and the spring pulling it back. This sounds like a
Ugh.
recipe for some seriously complicated movement.
It can get pretty complex.
How do we even begin to understand what's going to happen?
Well, that's where the beauty of physics comes in,
Okay.
That's where Newton's law comes in.
Yeah.
It helps us figure out who's winning this force tug of war.
Gotcha.
So if the forces are balanced,
Okay.
the block will either stay still
Mm-hmm.
or move at a constant speed.
Yeah.
But if those forces are unbalanced,
Uh-oh.
watch out. The block will accelerate, either speeding up or slowing down.
It's all about finding that balance, right?
Yeah.
That equilibrium.
Absolutely. Finding that sweet spot.
But friction seems a little tricky, I remember, from, way back when in high school physics, that there were different types of friction. Is that right?
You are absolutely right. We've got to distinguish between static friction and kinetic friction.
Okay. Yeah.
So static friction is what's keeping that block
Right.
stuck at the starting line,
Okay.
It's that stickiness you feel when you try and push a heavy box.
Uh-huh.
You need to apply enough force to overcome static friction to get that block moving.
It's like, how it's harder to get something heavy moving
Yes.
than it is to keep it sliding? That's what we're talking about, right?
That's the perfect example. Static versus kinetic friction.
And this model actually simulates that.
It does. That's one of the cool things about this model.
Wow.
Once the block is in motion, then kinetic friction takes over.
Okay.
And that's the friction that acts on the block as it's sliding.
Okay, so two types of friction, both working against the block.
Yep.
I'm starting to see how this could get complicated, but wait.
Yeah.
The ramp's tilted, does that matter for friction too?
That's where it gets really interesting. Remember how friction always opposes motion?
Yeah.
Well, if the block is sliding up the incline, friction acts downwards,
Oh.
trying to slow it down, right?
Uh-huh.
But when the block is sliding down, friction reverses its direction and acts upwards.
What?
Yeah.
So it's not just bouncing back and forth the way it moves up the ramp?
No, not at all.
It's actually different from the way it moves down
Exactly. It doesn't behave the same way going up as it does coming down.
because of friction.
All thanks to friction switching sides.
Friction, you sneaky little force. So we've got these three forces acting on this block.
Right.
In a kind of like a dance, I guess you could say.
Yeah.
With friction, even changing partners midway through.
Changing partners, that's a great way to put it.
But eventually they must reach some kind of agreement, right?
Yeah, eventually they reach a truce.
Okay.
That's what we call equilibrium.
Right.
Where the net force on the block is 0.
Uh-huh.
And it comes to rest.
I see.
And here's the thing. Friction is actually the peacemaker.
Oh, really?
It's essential for reaching equilibrium.
I always thought friction was just a nuisance. That slows things down.
I know it gets a bad rap, but...
Why is it so important for the block to stop moving?
Well, think about it. Without friction,
okay,
the block would just keep oscillating forever.
Oh, yeah.
Bouncing back and forth.
Right.
Around that equilibrium point, friction is what gradually drains the block's energy. Like a brake. It causes those oscillations to fade until it eventually settles down.
Wow, I never realized how important friction is for stability.
Yeah, it's crucial.
So it's not just about those three forces.
No.
It's about how they interact and eventually find balance.
That's what it all comes down to.
That's incredible, and that's where our simulation model comes in.
Exactly right.
It lets us watch this whole dance unfold and see how changing things like the angle of the incline, the spring constant, or the friction coefficients,
all those different factors,
affect the block's movement.
Yeah, it's really cool to see it all play out.
This is where we get to play with those control knobs.
Exactly.
In our virtual lab.
Yes, that's the fun part.
I can't wait.
Yeah, we can really experiment.
So in part 2, we're going to dive into the simulation.
All right.
We'll see what happens when we start tweaking things. It'll be fascinating to see those concepts come to life.
I think you're going to enjoy this.
I think so too. I'm really excited. I'm glad we're doing this.
Yeah, me too.
All right, so until next time.
Welcome back to the deep dive. It's time to fire up our virtual lab and see those forces in action.
I am ready. I'm ready to get my hands dirty.
Yeah.
So we talked about gravity, friction, and spring force, all battling it out on this inclined plane.
Right.
But how does this simulation model actually help us understand what's going on?
Well, imagine being able to actually see those forces in real time.
Okay.
As the block moves, the model shows them as vectors, those arrows, with length and direction, so you can visually see how strong they are and which way they're pulling.
Oh, that's cool. So it's not just a static picture.
Yeah, I know it.
We can actually watch those forces change as the block slides up and down the ramp.
You got it. It's like watching a mini-movie of the forces.
Wow. And not only that, but the model also gives us graphs that track the block's position, velocity, and the overall force acting on it.
Exactly. You get all this data.
What's the most surprising thing we can learn from watching the block's movement on these graphs?
Well, remember how we talked about the asymmetry in the block's motion? How it doesn't move the same way going up and down because of friction?
Yeah.
Well, that asymmetry shows up beautifully in the position graph.
Oh, okay.
The peaks and troughs aren't symmetrical.
Interesting.
The block might take longer to slide down than it does to slide back up.
So it's not just a simple bounce back and forth.
Oop.
The shape of the graph tells us something more complex is going on.
Exactly. There's a lot more nuance to it.
That's so cool. And that's just one of the things you can learn from this model.
Right.
Remember those control knobs we talked about?
Yeah.
The incline angle, spring constant, and friction coefficient.
Those are the fun parts.
Yeah, that's what makes this virtual lab so cool.
Yeah.
We can actually tweak the system and see what happens.
You can play around with it. So, for example, let's say we crank up the angle of the incline, make it steeper.
Yeah.
What do you think will happen to the block's motion?
Well, a steeper incline means gravity is pulling the block downwards with more force. I'm guessing it slide down faster and maybe travel further before the spring pulls it back.
You got it. A steeper incline, stronger pull from gravity.
Yeah.
You'd see those changes in the position and velocity graphs, bigger swings, faster speeds.
Cool.
And it might even take longer to settle down because it has more energy to burn off.
It's like making the ramp into a bigger slide.
Exactly. I love that analogy.
Okay, that's fun. What if we play with the spring constant?
Okay. Yeah.
Make the spring, stiffer.
Right. A stiffer spring is going to pull the block back with more force.
So it'd be like replacing a rubber band with a steel spring.
Right. That block would be zipping back and forth.
Yeah.
You'd see faster, more energetic oscillations.
Okay.
A loose spring, on the other hand, would make for slower, more relaxed movements.
I see.
And then there's those friction coefficients.
Right, the slipperiness settings.
Yeah,
So if we make the surface super smooth, like ice, the block will just slide more easily.
Exactly. Low friction, less resistance. The block will slide further, take longer to settle down.
Okay.
If we crank up the friction,
yeah,
simulating a rougher surface, the opposite happens. It slows down more quickly. Those oscillations die out faster.
So by playing with these settings, we can make the block behave in all sorts of different ways.
It's like a physics puppet show.
Yeah.
And the best part is, you don't need to be a physics genius to enjoy this.
Right.
The model is visual, interactive, so anyone can experiment and really get a feel for how these forces work together.
It's a great way to take those, abstract physics concepts and make them concrete, make them real.
Make them come alive. But, for those who do want to go deeper, we did mention that research paper in the show notes by Onorato, Mascoli, and D'Ambrosis.
Yeah.
It provides a more, a mathematical deep dive into damped oscillations and equilibrium.
It's there for those who want to explore the equations behind the curtain.
Exactly.
But even without the math,
this
simulation model is such a powerful tool.
It really is.
We've seen how changing just one thing can have this ripple effect on the entire system.
It really highlights how interconnected everything is in physics.
Okay, so we've explored the forces at work, played around in our virtual lab. But in part 3, we're going to blast off and take this system on a cosmic adventure.
Oh, this is going to be fun.
Get ready to see how our block and spring behave on other planets.
Can't wait.
All right, welcome back to the deep dive. We've explored the forces at play in our block and spring system here. We've tinkered with it in our virtual lab. Now it's time to take things interstellar.
I like it, going cosmic.
Yeah, fasten your seatbelts. We're going to see how the system behaves in some truly out-of-this-world environments.
This will be fun.
Okay, first up, the moon. Low gravity, very cool vibe.
Yeah.
What do you think will happen to our block and spring there?
Well, on the moon, gravity is about 1/6 as strong as it is here on Earth.
Oh, wow.
So imagine that downward pull on the block is suddenly way lighter.
So it's like the block is wearing moon boots.
Yeah.
It wouldn't slide down the ramp with as much gusto, right?
Exactly. Weaker gravity, the block would glide down the incline much more slowly.
Okay.
Those oscillations would be super stretched out like slow motion waves.
I'm picturing it moving with that dreamy, floating quality you see in those Apollo moonwalk videos.
Yeah, exactly.
That's great.
And, because the block would have less energy overall, it might take even longer to settle down to equilibrium.
Really?
Yeah, those oscillations could go on and on.
So a change in gravity. It's like changing the tempo of the whole system.
It really is.
It's amazing how something we just take for granted here on Earth, can have such a dramatic effect somewhere else.
It changes everything. Now, what if we go to the opposite extreme? Let's crank up the gravity, take our block, and spring to Jupiter.
Ooh, Jupiter. The heavyweight. I bet our block would feel like it was doing a high G training exercise.
Oh, yeah. Get ready for a wild ride. Gravity on Jupiter is much stronger than Earth's.
Right.
That block would plummet down the incline like a rock.
Yeah.
Those oscillations would be super fast and furious.
Like replacing the spring with a supercharged elastic band.
Exactly. And because of that intense gravitational force, the block would likely come to equilibrium much more quickly.
Really?
Almost like it's being yanked to a standstill.
So our block and spring system becomes a cosmic roller coaster.
It does.
Depending on where we take it.
It's fascinating, isn't it? How these fundamental forces just shape the behavior of objects.
Yeah.
Not just here on Earth, but across the universe.
It's like physics is speaking different languages on different planets.
It's pretty amazing.
But even though the effects might vary,
right,
the underlying principles are the same, right?
That's the beauty of it. The laws of physics are universal.
That's incredible. But let's bring our system back down to Earth for a minute.
Okay.
We've talked about these concepts in a pretty abstract way. Are there any, real-world examples where we see these forces at play?
Oh, absolutely.
Besides, shock absorbers.
Yeah, there's tons of examples. I mean, think about things that oscillate or vibrate.
Oh, okay.
Yeah. What about musical instruments?
Oh.
They're all about creating sound through vibrations.
Right. So like a guitar string, when you pluck it?
Yes. You're setting it into oscillation, just like our spring and block system.
And the pitch of the sound depends on the tension of the string.
Exactly.
Which is similar to adjusting the spring constant.
Exactly.
Yeah.
So tuning a guitar is kind of like adjusting the springiness of the strings.
I like that. And friction plays a role in instruments too, right?
It does. It helps to dampen those vibrations, shape the sound, and prevent the notes from ringing on forever.
Wow. So the music we enjoy, it's actually this delicate balance of forces.
It is. It's a symphony of physics.
I love that, a symphony of physics.
Yeah.
And these principles aren't just limited to musical instruments.
Oh, no.
They're at work in countless technologies.
Absolutely. From the tiny oscillators in your smartphone to the massive springs used in earthquake-resistant buildings.
Wow. It's mind-blowing to think that these seemingly simple concepts have such wide-ranging applications.
It really is amazing, the reach of physics.
We've learned so much about forces, motion, equilibrium, even gotten a glimpse of how these principles play out on other worlds.
It's been quite a journey.
It really has. It's been fantastic.
But, we want to leave you with one final thought. We've explored how gravity and friction shape our block and spring system. But what if we added a magnetic field to the mix? Or an electric field? How would those forces affect the block's motion?
That is a great question to ponder. It opens up a whole new realm of possibilities, it seems like, with physics. There's always more to discover.
Always.
More questions to ask.
Absolutely. So keep those curious minds engaged. Keep asking those what-if questions. The world of physics is full of amazing discoveries waiting to be made.
It really is. And that's a wrap for this deep dive. Until next time, fellow physics enthusiasts, keep exploring.
Keep exploring.